you a book of poems by a Chinese young poet who was with you practically in the Tiananmen period, young. You know it, and just obtained from Pescara a very famous flower.
E buon lavoro.
Now that the spiritual and the philosophical introduction is over, maybe you're ready for business on astrophysics. I'd like to call upon Professor Tita Chuck to present his paper.
So, I think you would not be so critical about my the first talk.
Not too long, because you need echoes.
Okay. Yeah, this is my problem. I'm too loud sometimes. So I lost my luggage yesterday, but unfortunately I did not follow my wife. She told me I should put my all transparents also in luggage, but I told her no, I should took them with myself. And this is only what I brought with me, this transparency. Therefore I can present my talk today. So today I have really 4 talks, and today I'm more prepared for the first talk, which is very fresh topic now. This is QPO phenomena, which maybe we should focus, yes. Oh, better. So, test. Okay. So So, because there is no really order in my transparencies, I did not expect I give talk in this, it would be the first talk, therefore maybe I have some mess with transparencies, but I try to do my best. So I just want to remind you who are not aware of this new observational results in power spectrum density of neutron stars binaries. 3 years ago, we found features. The first time we found features kilohertz oscillation. In addition to this kilohertz oscillation, we found features of 40 hertz, approximately 80 hertz, and also we found some correlation, all these features with kilohertz oscillation. During my talk, I tried to present you more comprehensive picture of all these phenomena, and the question is how these features are related. This is for SCO-X1 source. This is so-called Z source. And what is this? Why it disappeared? Okay. How these features are related with physics of neutron star system? How it's related with very important parameters of neutron star as mass, radius, and what it gives us information about mass accretion rate, and what we can learn about these features. This is very important, and where they come from. Because this is new things which of course was expected. You should understand kilohertz oscillation. For example, typical oscillation which we should expect from orbital motion matter very close to neutron star. It's for one solar mass, its typical orbital motion is about 1800 hertz, whatever. But how we can understand this phenomenon in general? For example, this kilohertz oscillation from one side is related with mass accretion rate. But it's seen when mass accretion rate is very low, and it's seen also when mass accretion rate 200 times more. And then when mass accretion rate increases and these features disappear, then appears once again. How it's related? It's from one side we see correlation, from the other side it disappears. In addition to these features, you see features, it's always, these features followed. When you see this, you see also frequency which is 40, 80 hertz. Sometimes you see these features, you don't see these features. How they related? How we can understand physics of this? Maybe this is the main observational facts which give us idea what is going on. Because if you look at, now it's very fashionable, at least up to this Rossi X-ray time explorer, which is called RXTE, it was understanding in astrophysics, in X-ray astronomy, to study of the system using only spectral features, not timing features, only spectral features. If you consider the whole phase space, how I call phase space, it's which is really reflection of the whole structure of your object. And of course, the main problem how we can restore structure of your object using spectral and timing properties. And if before this mission, X-ray time explorer mission, we study only spectral features and energy, but this is projection. You cannot restore one by one the whole features, I mean physics, because spectra gives you only projection, and from the same spectra, for the same spectra you can have very different geometric configuration. But timing is one-to-one in geometry. Time lapse, all these features is one-to-one geometry. And the main problem which I saw in astrophysics from a formal point of view, really we deal with inverse problem. This is a standard problem in science. Solution of inverse problem. How we can solve this inverse problem? Inverse problem, because our data doesn't allow us in many cases doesn't allow you to get something because data has their own dimension. And when people try to solve, for example, the simplest example is you try to solve one equation with 10 unknowns. One equation, and you play with the unknowns and try to catch flyers on the unknown elephant. This is typical situation. And of course, at first we should understand honestly what the dimension of our data space. What we can learn from this data space. This is the main problem in astrophysics, how I see. And now, timing for us, it's some kind of one-to-one correspondence with space. And next lectures, I showed you examples when, for example, energy spectrum are the same for compact configuration near black hole and neutron star and from very extended atmosphere. And energy spectrum absolutely the same. Energy spectrum really don't give you any information. But when you look at timing structure, like time lapse, variability, you immediately can see the difference. And I see a lot of activity in the astrophysics in the United States, in the whole world, when people try to fit using 10 parameters of the spectrum, they say something about nature of this particular object. And I see this is, of course, excuse me maybe for very strong statement, but this is cheating. This really cheating, and we should not cheat ourselves. We should understand formulation of the problem and then to proceed with solution. Otherwise, it's wasting time. So now, timing. As I told you, all these features have correlations. Correlations like this. Correlations like this. For example, all these features which I showed you, focus is not good really. This is main frequency, kilohertz frequency, and this is, for example, difference in twin peaks. How we can fix this, guys? And this is a difference in dependence on low 40 hertz peak, and this is 80 hertz peak. So, as I told you before, there are very strong correlation between these features. Another correlation between For example, so noise feature and Keplerian frequency. I want to just demonstrate observational results, and then we try to understand this. At first, you should pick up. We see in this power spectrum correlations, what I showed you. If I found my transparencies, as I told you before, at least I try to do this. Okay, I found the main transparencies. This is very good. So, correlation. Now, because I found this transparency, the whole picture would be very clear. So, I try to explain and then to illustrate. So, we have this power spectrum. Once again, all features together. All features together in these transparencies. Power spectrum multiplied by frequency is real representative and versus frequency. So we see high kilohertz QPO peak, low kilohertz QPO peak. We see two features, 80 hertz approximately, this for Coaxial 40 hertz, so-called noise feature, and this is break frequency. This is frequency which I showed you before, this power spectrum with some kind of break when plateau is followed by some power loss. So, and how we can understand this feature in terms of geometry, general geometry. And I try to explain this using this picture, and then I illustrate in terms of some kind of mathematics. So what we really have in the any binary system, we have a central object, we have some disk, we have some kind of magnetosphere for neutron star, and with question, some kind of magnetic field near black hole. It's also some kind of possibility. People discuss and consider this very seriously. But can we get this directly from observation? This is my point. Can we get without any fantasy this precisely presence of magnetic field near black holes? This is very important. One thing to elaborate some budget, whatever energy, another thing have direct measurement of magnetic field in terms of similarity, in terms of correlation, everything. This is very important. A lot of speculation, a lot of papers, but I never seen any proof. Now I try to convince you in a very consistent way we can extract comparing neutron star, black hole versus vice versa, and understand all these features. So, let's start from very generic. We have central object, we have disk. At very far away, this is Keplerian. You have a circle orbit, and after that, it's like adjustment C to the beach. And you know, if waves are very strong, if velocity in the sea is very strong, finally you produce some kind of wave very close to the coast. What is this reason for this? Because sea should adjust to the beach when velocity is zero. The same here. You have Keplerian disk very far away, and finally this Keplerian disk should adjust to sub-Keplerian boundary conditions. This is absolutely generic. So, what is this adjustment? Adjustment, of course, you can formulate mathematically this adjustment. You can formulate generically this adjustment. You have Keplerian motion, you have sub-Keplerian boundary conditions. For sub-Keplerian boundary conditions, for adjustment, you formulate at least three boundary conditions. One, angular velocity, it's as a rotational velocity of neutron star. It's one boundary condition. Another boundary condition, adjustment very close to Keplerian disk. Its values should be the same from left and right in this adjustment radius. And also derivative should be the same if this smooth adjustment. But this is marginal smooth solution. You understand? If you even have some kind of breaking derivatives, you produce some kind of wave here, and you should pass through super Keplerian motion. You always produce some kind of wave in this point. So, exchange of angular momentum in general, it's diffusion process. Diffusion process, you just exchange by angular momentum, which is described by second order differential equation. You should understand this. This is typical diffusion equation. Second order differential equation, and you have three boundary conditions. If you have three boundary conditions for the second order differential equation, you have this particular radius when you adjust Keplerian disk to sub-Keplerian boundary conditions. This is generic. So, you have with given Reynolds number, because Reynolds number is only parameter which regulates this adjustment. Reynolds number, I just remind you, it's a ratio of your velocity, radial velocity size, turbulent velocity, and turbulent size. So this is the Reynolds number which regulates this adjustment. Not mass accretion rate, nothing. This ratio. Okay? And depending this gamma, I illustrate in terms of equation, but qualitatively I explain it. Depending on this Reynolds number, you have position of this adjustment radius. So you should expect correlation between adjustment radius and Reynolds number. Okay? What is the next point? You produce this wave, this barrier, and matter coming and hit this barrier, and of course we considered this problem with Sandeep Chakrabarty 5 years ago. When we produce some kind of barrier general, you release gravitational energy there, and you have balance really due to cooling. You release energy, you heat material, and then you cool by Compton's electron scattering. And therefore, you can write this balance and calculate temperature. And temperature with assumption of this electron scattering and free process, emission and absorption, you calculate this temperature much higher than 1 keV, 10 keV. It depends on mass accretion rate. This is very important. If you have 5 keV here, but typical temperature for the disk fraction of keV, that guy immediately bounced. I mean, this piece of matter near adjustment radius immediately bounced. If magnetosphere is there, it's this guy, piece of matter here near this radius immediately thrown away in magnetosphere and pick up of magnetosphere, which is rotating. So we have, from generic point of view, I try to repeat to you once again, you produce this blob, no doubt about this. This blob thrown away to magnetosphere, it's picked up by magnetosphere, and what is the result? When you throw away this blob oscillating. If you consider potential field, it should be oscillating in 3 dimensions. It's trivial. You can write a Newton equation and you can prove oscillation of this blob would be in 3 dimensions. But in the presence of magnetic field, if magnetic field is compared with gravitational field, which is precisely the case when magnetic field 10 to 9 Gauss, I can demonstrate you, we can expect even only radial oscillation. Only radial. There is such solution. when oscillation over z coordinate and azimuthal coordinate is suppressed, and there is only oscillation in radial direction. There is self-similar solution for the appropriate MHD. So we have generic. What we can learn from the generic? What we can learn? So, what we can learn? Let's consider this is only radial oscillation in rotation frame of reference. This Keplerian oscillation would be split under influence of Coriolis force. If you write second law of Newton, you immediately see there is additional force in rotation frame of reference. And some people argue rotation frame of reference relates with magnetosphere, but we are in infinity. What is the reason to consider rotation frame of reference? What is the reason to consider this? Reason is matter is rotation frame of reference. All observational appearances related how density, how temperature, they related each other, how they change. Therefore, what we see, we really see change of geometry, we see change of density, all physical parameters in rotational frame of reference. Therefore, there is reason to consider this frequency. Now, what we can get from this? I just remind you this stuff which I told you. So we should write equation. Unfortunately, now we should refer to equation. This is equation, 3 equations for each coordinate. We consider only oscillation in radial, which is x, and this radial oscillation in x coordinate or along radius, and Coriolis force. So this is very simple problem which you can solve and try to find oscillation mode. You should write dispersion. You should look for solution in terms of oscillation, and finally you can come to dispersion equation. This dispersion equation has stable solution which we don't care, I mean, when frequency is 0, and oscillation solution. What is this oscillation solution? One is so-called hybrid frequency, which is square root of Keplerian frequency plus 4 square of rotation frequency. This is the upper frequency. And another is low branch frequency, which is related with angle between a rotational axis and normal to the disk. Because we consider only a linear equation, we have 2 frequencies. But of course, because we deal with weakly nonlinear oscillator, and therefore in this weakly nonlinear oscillator, we should expect terms of the second order and the third order. If you include the terms of the second order in this weakly nonlinear oscillator, you should expect terms which is so-called combination frequencies, which is double of this frequency, difference and sum. So, really, look at once again to this figure, the main figure. So we found hybrid frequencies as a solution of this problem. We found low frequency and double as a result of nonlinearity, weakly nonlinearity. Now, we found this and we want to find its number. But we should reproduce function. All these frequencies are related with Keplerian frequency, which you saw. I just remind you once again. You see? All these frequencies which we reproduce using this model, this hybrid frequency and low frequency is related with the main Keplerian frequency, which is just frequency of this one-dimensional oscillator. And can we reveal this dependency in observations? So, the first, using these two peaks which we observe, we can extract from observations rotational frequency of magnetosphere. This is very important result. You should understand this. For example, if we see this splitting for black holes, or we don't see this splitting in black holes, there is the question for existence of magnetic field around central object. And that guy should be, if almost constant or changing of this, and I should remind you, history. When this effect was found, people say, oh, we have one peak and another peak, and difference between them can be interpreted as a deep frequency effect. You have oscillation of your blob, which is affected by rotation of star. If you beat some kind of blob on neutron star surface, of course, this beat frequency effect and the difference in two peaks, it should be rotation frequency of neutron star. But in observation, nature is more sophisticated than people thought. This difference is not constant. It's changing 40%. And the question is this rotation frequency of neutron star is changing 40%? This is ridiculous. You just calculate energy budget and you immediately understand this is not physical. Why difference between two peaks is not constant? If we are right in this model, when upper frequency is produced due to Coriolis force, of course this is not constant. Upper peak is square root of Keplerian square plus 4 square of rotation frequency. Can we prove this using observations? So, these observations, we extract frequency, this rotation frequency, using this hybrid relation. Key point. These two sources, 1702, one source, 3 observation points, and SCOX1, 39 points. If you use this upper hybrid relation, you found rotation frequency of magnetosphere is almost constant, and blob really for different Reynolds number just probing magnetosphere in different places. I want to remind you. You see, you have this different Keplerian frequency at each moment. Really, you have cross-section, this cross-section for given moment, and you observe this system in different moments, and because your Keplerian frequency is directly related with Reynolds number, which I demonstrate you later, maybe next lectures, if you have some question, but you have to understand this, you have to have in mind this picture. Really, for different mass accretion rates, you have different Reynolds number, and for given Reynolds number, you have particular value of adjustment radius there for when you throw away this blob, you probe this particular place in magnetosphere. And for this particular place in magnetosphere, you can reveal rotation frequency of magnetosphere. If you use this hybrid relation, you found this rotation frequency. And you see it's almost constant with some kind of weak variation for Coaxial, and because we don't have enough for 1702 source, we have almost constant frequency. This is one point. Another point is, you can ask me, how it's related with rotation frequency of neutron star? This is another question. This, for example, 380, and this frequency is 340 Hz. And of course, natural question, can we find rotation frequency of a neutron star itself? The question sometimes is positive, sometimes negative, because it's related not with our fantasy, it's related with observation. Can we find this rotation frequency, and when we can find this rotation frequency? At first, this frequency should be very coherent. It's one thing. Then we can believe this really rotation frequency of Newton. And the second, we should find event for this particular source when we really deal with rotation of neutron star. And this particular event is burst. During burst event, when matter just expanding and contracting and subsiding on neutron star magnetosphere, we can believe in this case what we see as a oscillation effect with very high coherence. This is really rotation of neutron star, and precisely for 4U1702, this frequency is observed, and frequency is not 380. Frequency is 333, much lower than this. So we see spin-up magnetosphere, but neutron star rotation is much lower. And really, we see only some part of magnetosphere, and we don't see some kind of innermost part of magnetosphere. We're probing in some particular region, some particular area of magnetosphere. And question is how they adjust each other. How much time I have? 10 minutes? Okay. I should not I try to reproduce for you main features, and Professor Ruffini told me I can spend some time. Yeah. So this is another source. It's written somewhere, but this is another source, if I remember, for you 1608. For which, I just remind you once again, for this source, we also see variable separation of two peaks. Upper peak and low kilohertz peak, variable. When you use this hybrid relation, you found very similar feature for Coaxial, and it's not fitted by function where constant is dominant. Changing of even rotation frequency is quite significant. This theoretical curve, which we feed, theoretical curve, really there is some kind of science behind of this. You can prove rotation frequency of magnetosphere is a function of Chandrasekhar potential. And Chandrasekhar potential can be presented by multiple presentation, multiple expansion, yes, multiple expansion. And for this fitting of observational data, we use dipole and octopole. And you see how this expansion describes observation points. But this approximation we can discuss later, but important thing, we can reveal a profile of rotation frequency of magnetosphere, and for this we use just dipole and octopole, like for Coaxial as well. So, next point is test of this model. Test of this model. What is the test of this model? Okay, we use upper kilohertz peak and low kilohertz peak. We reveal frequency, rotation frequency, and next point is, can we check this or not? Because we have another peaks and correlation between them. It's impossible to cheat. If we start from this point, we should follow this way honestly, or some point when we disrupt it, you should say honestly, it doesn't work. And unfortunately, I found in many cases in astrophysics, people don't want to say this. We are wrong. They try to adjust all the time, introducing new parameters. Now, we see correlation between upper kilohertz peak and frequency frequency around 4 hertz and 80 hertz. We see this correlation. Okay? This relation, low branch relation, which is here. So what we have here? We have hybrid frequency, we have Keplerian frequency, we have angle between rotation axis and normal to the disk. This really, when we reveal profile, rotation frequency profile, we have this hybrid frequency, or vice versa, is a function Keplerian frequency. And when we calculate dependence of this low frequency versus Keplerian frequency, we should get some specific dependence. And this dependence should be checked by observation. We check this. This solid line is this theoretical dependence for particular angle, 5.5 degrees for Coaxial. We demonstrate not only test of this model, we also demonstrate we can reveal parameters about system. How magnetic axis or rotational axis of neutron star is adjusted during evolution to normal of the disk. And from general point of view, we understand this adjustment should be quite perfect. Angle should be small. And we get this. Angle really small, with very high accuracy. Angle is delta is 5.5 plus minus 0.5. What we can learn from this? Now, because maybe I adjust, how much time I have? 5 minutes, okay, I will present. So I just remind you, summary of this part. So, what we did, we just extract information about rotation frequency using 2 peaks, and then we reproduce a profile of low frequency branch versus Keplerian frequency. And we just test model and reveal very important physical parameter, angle between rotation axis of magnetosphere and normal to the disk. Now, I just remind you about second part, about this transition layer between Keplerian part of the disk and neutral star. I told you by words, but I just demonstrate you equation which describe exchange of angular momentum in the disk. This is the second order. You have question? If you have question, you can ask. Yeah, you have second order differential equation here. This is really second order differential equation because this terms are also derivative. You have main parameter in the first equation and the Reynolds number, which I described you. You have also parameter which is related with the parameters of neutral star. It's Keplerian parameters AK, it's written here. And you have 3 boundary conditions, which I described here. You have 3 boundary conditions, which I told you by words, but it's described here. So, and inner on the surface of neutron stars or magnetosphere, and 2 boundary conditions at adjustment radius. And finally, because this second order differential equation, you can determine adjustment radius. And you should expect dependence of adjustment radius. You should expect correlation between adjustment radius and Reynolds number, and Reynolds number related with mass accretion rate if you relate mass accretion rate with radial velocity. So finally, you have 2 characteristic time in this adjustment radius. It's just oscillation of this transition layer, which is in dimensional units is just size divided velocity, and diffusion time, if it is square size divided velocity. It's also generic. Next question, how we can translate these 2 characteristic time in gamma parameters. We just say radial velocity in this particular part of the transition layer is related with gamma parameter, which is the parameter of this Reynolds number, which we can reveal because gamma related with Keplerian frequency, and we have this dependence in terms of frequency. The first parameter is time, characteristic time is just frequency and inverse, and break frequency is inverse to diffusion time. So, let's check. At first, because of this relation between two characteristic frequencies, we should expect correlation. And this is observational correlation. This is point observation correlation between this break frequency is diffusion frequency and viscous frequency, I mean oscillation frequency. And this is dependence, observational dependence. And this solid line, what I found as a solution of this problem. This particular index 1.61. Break frequency nu b is this. Sorry about this. Reflection effect. So we have this theoretical correlation between two frequencies, and we see this observation correlation for particular source coaxial. Only for coaxial. Next point is, can we found this correlation for other sources? This bunch of sources. This is so-called atoll sources, all together. Radio pulsars. As they demonstrate the same dependence. All of them. And describe the same relation. Because our consideration was generic. We don't introduce some kind of dependence. Generic. It's revealing many, many sources. Now, life is more complicated, which we think. This is atoll sources. Another branch is this source. These sources. All these atoll sources and radio pulsar described by this relation, but we have another branch, which is low. But if we multiply by these points by factor 4, we found all these points in the same line. Is it by chance or not? I just want to remind you, this transition layer when we have diffusion. But diffusion is described by initial value problem, Cauchy problem, which is sum of exponential shocks. As the main fundamental mode is different from the second one in terms of characteristic time by factor 4. I can demonstrate you right away, and therefore we have, when we multiply by factor 4, we get this dependence. In order to complete my talk, I want to demonstrate now classification picture. When we bring together all these frequencies, this is 1728 source, all frequency together versus Keplerian frequency and dependence, using this theoretical description. And we found all observation points going along theoretical curves. Maybe it's just by chance. Another source, Coaxial, the same story. All observation points going along a theoretical point. And another story. 1702. Maybe we deal with complete classification of all these observation features. Really, we have another 2 more features like 5 Hz, 1 Hz, very stable frequency. And I don't have time to discuss now, but we can discuss later during our session. But definitely we deal with situation when we can reveal the main physical features or parameters or at least neutron star, and we can hope we can understand situation near neutron stars, then can proceed to black holes and produce comparative analysis of these observation features versus theory. Thank you very much.
One question, please. And your model has the weight of the block.
Width is very simple. You mean width of all this? Not only width, shape, even shape. Yeah, because this is trivial. Yeah, this is trivial. Shape, at first you should describe power of this line. What's this power of this line? You have 2 processes, diffusion process in this transition layer, and you have oscillation. Okay? And therefore you can immediately derive power for exponential for short, which is described by exponential sign. And of course, in this case, you reveal the whole story. I mean, shape and width right away. And I don't have these figures, but I can demonstrate all this analytical description perfectly observation point. And width, of course, is described by motion. It's Doppler effect. Excuse me? This is very important question, really. Of course, you know, Sandeep, I don't need even to say you. We cannot reveal real mass accretion rate. We can say mass accretion is changing by factor 10 or 100. And I can answer in this way. We see this guy. When mass accretion rate is different by factor 100. But it doesn't matter because Reynolds number is the main parameter. And Reynolds number does not care.
You don't want to cool those blobs very quickly, right? So you want to keep them hot, and so that...
Yeah, it should be hot.
Yes.
But if from our solution, you remember,
yeah,
it doesn't matter mass accretion rate.
No, but if the accretion rate is high, let us say more than 1 Eddington rate or 1, then that blob is going to be cooled. So you should see these things only in the hard state, only in a very low accretion rate region, then only they remain hot. If the accretion rate is high, you are going to cool them.
Absolutely, you are right. But you remember our situation, our mass accretion rate or luminosity can be changed by factor 10 to 1,000, and you have the same old features.
Yeah, as long as it is very small.
Absolutely, you are right. If mass accretion is very high, all these features disappear.
Okay, then I agree with you.
Yeah, of course you agree.
have some adjustment on it? I found that a very loud talk, Lev.
Yes.
I'll be thinking when I fall asleep, I'll hear your voice booming in my head. Is there adjustment in this? Or just I can just position this as needed? And there's no volume. Okay, I can do that. Well,
I told you, I don't like that.
well, let me know if my voice is too loud, because my voice projects as well. Let me know, and I can maybe adjust the position of the microphone. Just raise your hand if this is annoying you. I have no idea how loud it is over there. My talk today is really an extension of what I started talking about yesterday. It's a follow-on to that talk. And some of you weren't here yesterday, so let me just review what that was in a couple of sentences. I proved a no-hair theorem for accreting axisymmetric electromagnetic sources in the curved space-time. And the implication of that no-hair theorem is in terms of the membrane paradigm, is that the horizon does not behave quite generally like an imperfect conductor. It only appears to when the hole is passively accepting information. So you see the impedance, the resistivity of empty space, surface impedance 4 pi over c that you get from displacement current. But there's a big difference. It can't radiate to L bigger than 0 moments of the electromagnetic field, which a unipolar inductor could do, or a rotating conductor. So I proved that the space-time behaved quite generally for these axisymmetric electromagnetic sources that are charge neutral, behave quite generally as if it were an asymptotic infinity. And I want to continue that talk because the main place where the infinity interpretation disagrees with the membrane paradigm is whether the black hole can actually operate the event horizon, not the extended region far away, but the event horizon proper can operate as a unipolar inductor. And the argument in the membrane paradigm monograph is that since a black hole can be torqued like a rotor, where it's absorbing information, this was a thought experiment first done by De Moor. If you think about what we talked about yesterday, you can just send in, put the black hole in a uniform magnetic field and send in currents in a way that's asymmetric, pi asymmetric from chemistry, if you remember that term, asymmetric in the northern and southern hemisphere. So you send in a different angular momentum flux with the ingoing wave from the northern hemisphere than you do from the southern hemisphere, and you get a net torque on the hole. That's how the hole acts like a rotor. Just absorbs 2 electromagnetic waves asymmetrically from the different hemispheres. So what the membrane paradigm has said, well, let's just turn it around, and we can recreate the Blandford's-Nodgic mechanism. We say the event horizon can act like a unipolar inductor and emit radiation. Now, first of all, this conflicts with our no-hair theorem that says the horizon can't radiate multiple moments. And it also conflicts with causality within the leads themselves when you try and connect them to the horizon, because the propagation of information within the leads has to go in terms of some kind of mode. And those modes would be the plasma waves of the lead material. And those are definitely less than the speed of light, so you can't send waves from at the tips near the horizon out to infinity. So the tips can't communicate to infinity. And again, this is a fundamental difference between the two, the infinity approach and the membrane paradigm, and it's motivated by the Blandford's-Nodgic model, which was motivated by the MHD pulsar model. And so within the two models, the black hole behaves just like the pulsar does. I mean, the neutron star and the pulsar. So that's the motivation for this, and so we want to clarify this. So here's what Thorne envisioned, the simple little diagram here. Just assume this is a black hole. We have a uniform magnetic field, or some magnetic field, an equatorial conductive disk, and a wire coming into the pole. The idea is that they talk about having a load at infinity, but that doesn't really matter. Within the membrane paradigm, this configuration would radiate Poynting flux. You'd have an ammeter here. You'd see current registers, just like you're rotating a copper sphere down in this region. Again, this will just radiate like a pure electromagnetic waves. In this case, it's a vacuum. So you don't really need a load out here. They always talk about loads. In this case, the load would just be 4 pi over c. It's the surface impedance of the vacuum at infinity, just like we had at the horizon. And so the proper way of thinking of this is not in terms of a DC circuit, because you don't need a resistor in it, and plus it's very awkward having wires going in and out of the hole. The right way of thinking of it, a better way at least, for analogy's sake, is thinking in terms of like transmission line theory, where you don't need resistors and stuff. And so we'll talk about analogies in terms of transmission lines and waveguides, plasma flow waveguides. So, as I say, it's more appropriate to think of this in terms of an open-ended transmission line because it's a radiation problem. And there's this analogy to the unipolar inductor where the fictitious, remember we had fictitious surface currents on the horizon in the membrane paradigm that just basically shut off any tangential magnetic field. It's a mathematical artifice. But the question is, do these fictitious surface currents act like the physical currents in a Faraday wheel? Do they mimic the behavior of the physical currents in a Faraday wheel? Secondly, it's claimed within the membrane paradigm that since there's a voltage drop across magnetic field lines at the horizon, this is a battery-like EMF that can drive a global circuit. So these are the things we want to analyze, these statements. And of course, with the no-hair theorem, we'll find that they aren't really true. But we want to understand why they aren't true, and we really want to understand what a unipolar inductor is, so we can really make that comparison very clear. So what I did is I started an investigation of the unipolar inductor, and a lot of this will be laboratory-type physics that I'm going to talk about. So imagine a long solenoid with a uniform field and a little rotating disc inside. The rotation of the disc produces an EMF, a B cross B force, that gets canceled by a surface charge distribution. So this is the electric field that cancels the B cross B force, and here are these straight lines right here. And it makes a quadrupole electric field. So that's just the rotating disc in isolation. This is the Faraday. This will be the Faraday wheel when it's attached to a circuit. That the analogy of the event horizon in the membrane paradigm is compared to. So we want to understand this pretty well. First of all, in any circuit, the unipolar inductor, this rotating disc, will establish the voltage drop in the circuit. And the reason why current flows in the circuit is because when you attach the leads, you no longer can have an electrostatic equilibrium. When you attach the leads to the edge of the edge of the disc, well, now the surface charges on the edge of the disc will induce electric fields into the leads themselves, and that'll move charges and pull charges, the surface charge, off the disc. Suddenly, you don't have enough surface charge to make an electrostatic field that balances the V cross B EMF, so there's a slight unbalanced EMF in the disc, and that'll drive more charges to the surface to try and balance it off, to kill that EMF off. But again, that'll induce charges in the wires to flow, and so you have this non-equilibrium situations where current flow once you attach the leads. So that's the physics of why current flows. You've broken the possibility of electrostatic equilibrium. You've introduced a new degree of freedom to the system that allows electrostatic equilibrium to be not to exist. And that won't be allowed in the black hole case. That's a key point. So let's start looking at the Faraday wheel that terminates a transmission line, because that's a good analogy. And then we'll look at waveguides as well. And this will give us some wave structure and really elucidate what the unipolar inductor does. So here we have our, that's not the, so is the focus on this pretty good? Does anyone know how to focus? Because I know on here the type looks good, but I'll just describe what these are. This, I don't know if you can read it. Can people read this as coaxial transmission line, or is it just too fuzzy? It's too fuzzy? I would think that you could focus this thing. Is that it? Focus lock. No, that means, we should be able to get better quality, but I don't know. Unless someone comes in here and knows how to operate this, so I'll just leave it as is and just continue talking. and describe what these things say. So here's the coaxial transmission line inside of a long solenoid. And here's a blow-up view of the transmission line. And what we did is we fit a rotating electrical disc that's making rotating conductive disc that's making electrical contact with the center conductor and the walls of the coaxial transmission line. I left on here the electrostatic field of the disc, that's the dashed lines. And the configuration that arises is that the disc now drives a current system. Currents come in along the center conductor, out along the disc, and out along the outer conductor. And the electric field configuration are the solid lines. It makes a toroidal magnetic field, and a Poynting flux goes outward in both ways in the transmission line. What this field is, it's the omega goes to 0 TEM mode of the transmission line. So between small omega and big omega, there is no difference. The structure of the TEM mode is one that's very interesting. It's the simplest mode you ever have in any kind of wave pattern transmission line. It keeps the exact same form at all frequencies. It's just the fact that this is now a static configuration. It's not really a wave. It's the limit. It has the exact same electromagnetic structure in terms of B phi and the radioelectric field that the TEM mode has, but it's not really a wave anymore. That's what the omega goes to 0 limit means. That the electromagnetic structure is exactly the same. The TEM mode has the same magnitudes of B phi and the radioelectric field. The interesting case for the black hole is this case, the disconnected. This is that's a shame it's not focused. A disconnected transmission line. You take the transmission line and pull it away from the disk. So now currents can't flow. And this is exactly what the black hole is like, and we'll talk about that later. Remember, the leads never touch the black hole. They can never get down there. It takes an infinite amount of time to end up with this type of configuration. So what do we see here in this? Here's the center conductor. Here's the outer conductor of the transmission line. Here's the Faraday wheel. We have an electrostatic configuration. We have, here's the electric field in the disk. There's a voltage drop across the magnetic field lines in the disk, yet no current flows. So the voltage drop across the magnetic field lines is not necessarily equivalent to a battery-like EMF that drives a current. That's the main lesson of this. The other lesson is that we drop this voltage drop in computing integral E dot dl to electrostatics equal to 0 in these gaps over here, and the voltage drop is equal to minus omega the disk phi over 2 pi, just to give it a value. The next question to relate to the, which will distinguish the difference between the unipolar inductor and the horizon, is we take the transmission line and let it slowly approach the disk. Well, if you do that, the electric field will diverge like 1 over d, this gap right here. And eventually the electric field is going to be strong enough that it's going to rip electrons, these E minuses, out of the conductors and make sparks. And once those electrons are ripped out, currents will start to flow. There will be a little resistivity associated with those sparks, but the current starts flowing and you end up back with this configuration again. And you start launching these TEM modes. So that's the lesson there with the disconnected transmission line. So to summarize, with the Faraday wheel in a transmission line will radiate the TEM mode and the omega goes to 0 limit. The open-circuited transmission line has a voltage drop across the magnetic field lines, but no current flows. There exists a local electrostatic equilibrium. If you try to take the transmission line and slowly get it closer to the rotating disk, the electric field is going to diverge like 1 over the distance of that gap. Spark gaps will occur. There'll be the breakdown of electrostatic equilibrium. Currents will start to flow, and the TEM mode will be radiated at that point. Now, a more interesting example is a Faraday wheel that terminates a plasma-filled waveguide, because the plasma-filled waveguide will be an analog to the black hole magnetosphere. So again, we do the same type of construction. and the focus still isn't that good, so I'll describe what's in here. Here's the plasma-filled waveguide inside of a long solenoid, and here's a blow-up of where we put a rotating conductive disc with the plasma-filled waveguide above and below. The stippling indicates the plasma. Again, I've indicated the vacuum electric field to the disc by this dashed line. And what happens is you get a wave radiated that has an electric field. I realized when I did this, I never realized before that you can't really draw electric field lines in a plasma because the electric field goes to zero here in these modes. And so I just indicated by two arrows. These modes are well defined. They're just Bessel functions. And what we get is that we got the toroidal magnetic field, and the solid lines are the radioelectric field. We get a pointing flux going both ways out of the waveguide, up and down. Currents flow. Instead of the return current, we have currents flowing from the disc up along the outer conductor, but the return current, instead of flowing along the inner conductor, now flows through the plasma itself. That's this eye over here. What this wave is, it's the omega goes to zero limit, this is very important, of the Alfvén wave, the shear Alfvén wave. These plasma-filled waveguides were studied by Stix in the late 50s, cylindrical waveguide, and it's in his book on the theory of plasma waves. He has a chapter on it. Very important point is that the omega goes to zero limit in this plasma-filled waveguide. The fast compression wave, what we normally call the fast wave, is cut off. It does not propagate. This information from the disc here is purely an Alfvén wave. It does not depend on the fast wave at all. It's a very important point. So the Alfvén wave is a very important radiation mode for the Faraday wheel. So now we look at the relevant case of the black hole. We disconnect the plasma-filled waveguide from the rotating disk. Again, we establish an electrostatic equilibrium. I put a very thin Teflon sheet here, which is a good dielectric to keep the plasma in the waveguide. We have an electrostatic equilibrium. Here's the disk again. We have a voltage drop across the field lines in a disk, yet no current flows. So again, having a voltage drop across magnetic field lines does not necessarily mean you have a battery-like EMF and drive currents. We take again, the whole voltage drop is dropped in this gap over here if you do integral E dot dl equals 0. And the next thing is to take the plasma-filled waveguide and slowly approach the conducting disk. Just as before, the electric field will diverge like one over the gap. Eventually, you'll have spark gaps forming, and the currents will start to flow, and you end up back with this configuration again with some resistivity associated with the sparking, and you'll start radiating Alfvén waves again. So that's what happens with the unipolar inductor. One other thing about this solution we can learn, the plasma-filled waveguide, if with T equals 0, we just insert the rotating disk into the plasma-filled waveguide. So that's when the contact is first made. We look at a later time, and what we have is the Alfvén wave being shot up the waveguide, but there's a flow front. And the flow front has a displacement current at the flow front, which effectively closes the circuit. It's very similar to what happens at the event horizon. You have a current going this way up here, and the whole circuit closes with displacement current at the flow front. Return current comes down the center, and here we got the electric field and B phi written on here. There's a pointing flux. And here's the calculation where you can see what the displacement current is. And in the limit, this is moving very fast, like the speed of light. So that again motivates the reason for looking at, instead of DC circuits, looking at transmission lines, because they're still going to radiate. So what do we learn from this? That the Faraday wheel and the plasma-filled transmission line radiates the omega goes to 0 torsional Alfvén wave. The fast compressive mode is cut off. We'd expect a black hole magnetosphere to have some kind of cylindrical topology, and maybe something similar might happen there. What we have is that when it's open-circuited, we still have a voltage drop across the magnetic field, but no current flows. It's an electrostatic equilibrium. As the gap gets smaller and smaller, you bring the plasma-filled waveguide near the rotating conductor, it'll spark, or an Alfvén wave will be radiated. So let's look at the black hole analogy. What we're going to find is there's a voltage drop across the magnetic field near the horizon. No current flow will be generated. It's totally similar to an open-circuited transmission line. And the gist of it is that the horizon voltage drop cannot be used to power a global circuit or relativistic jets. And that's what I want to show here. So the first thing is these thought problems. How do we attach the leads? Well, the leads actually interact with the magnetosphere. This is where you're hiding all the physics. These thought problems are way oversimplified. And so all the physics of the ergosphere is really missed because the leads interact, and that's where you get the interaction between the black hole geometry. But so we want to try and separate out the unipolar properties of the leads from many unipolar properties that the near horizon space-time might have. So we have to be careful how we attach the leads. So with the configuration of Thorne in the membrane paradigm, you end up with an electrostatic equilibrium that looks like this, very similar to our disconnected transmission line. But the problem with this is the flow in the equator is so complicated. You're bringing a conductor across a magnetic field, so that interaction is huge, and it has to be separated out. So we need to pick a simpler configuration than that. This is the event horizon right here, this surface right here. So the flow will never make it to the event horizon as seen globally. So there's always a gap there. That's the point. So, yeah. Well, for this configuration, the way I would do it, and I describe it in a paper, is the only way you could do it is you would have the lead at the pole be a wire or just plasma falling. You have plasma falling down a flux tube at the pole, or you could have a wire on a spool that can just spiral freely out, and just the wire would just pull off and just start approaching the hole. In the equator, you need a liquid conductor like mercury. These are the complexities of these simplified things. You need something that can actually have enough collisions in it that it can cross the field easily. You couldn't do it with a gas. I mean, it can't get across the field line. The field's too strong. So you need something that can penetrate through. And that makes this problem too complicated, so I'm going to make a different problem. It's a little bit simpler of attaching the leads. But the whole mechanism of attaching the leads is the problem that needs to be solved. There's no way around it. You just can't say, look at the boundary at the horizon, forget about how the leads are attached. You're missing the physics. So what I'm going to present here is actual mathematical proof that when I isolate the horizon part out, it doesn't do anything. And we're going to have to later on look farther out in the ergosphere with interactions with the leads to find out what's really going on. So I'm separating that part out. But attaching the leads is, in a perfect MHD sense, is probably impossible in almost any configuration you can use. So I'm going to use the Faraday's law and the 3+1 split of Thorne to show that the horizon is not, doesn't act like a unipolar inductor. So here's the Faraday's law and the 3+1 split. You have an extra term due to the dragging of inertial frames, so to speak. This term here, it's the velocity that the ZAMOs see. So it's really the angular velocity of the ZAMOs times the metric coefficient. If we pick a integration contour, as we were, that's stationary with respect to infinity, you have this extra term. Here's the magnetic flux derivative. And then we have a key part of this calculation. I'm actually going to show the steps in detail, but these are the main pieces, is that since the flow is going in relativistically fast as seen by a ZAMO near the horizon, and the ZAMO frames, E theta is equal to minus B phi. That's the ingoing wave condition that Thorne talks about. No matter what currents are flowing or surface charges are on the leads, you always have that situation. When you do the line integral, we're going to get that the electric field in the gaps is well behaved. It'll equal this, the theta component of the magnetic field will be well defined. But the point is, and I'll show you all these terms in a second, that the radioelectric field stays finite. So the radioelectric field in the gap does not grow as the horizon is approached as it does for the unipolar inductor when you bring the transmission line next to it. So this is the simpler configuration that I wanted to look at, and still this configuration is very complex. We'll have the polar lead, which is always easy to attach, and then we have a lead over here near the equator, which I'm going to let be plasma that's sliding down a flux tube, kind of like the walled field. And So here's going to be the contour of integration. We got break into 4 pieces, B, C, D, and A. And we'll do this line integral and the surface integral, the magnetic flux in here, and we'll compute the radioelectric fields in here. So, is this for me or for somebody else? Okay, yeah? Yeah, we can. Oh, using observations? No, you can't, because any model of a black hole magnetosphere, the end result, you're going to have a dimensional analysis. It's like going to be some fraction of the angular velocity of the hole squared is going to be in the Poynting flux to infinity for a relativistic flow. So you, in terms of astrophysically, the answer is complicated. I have found a way to tell the difference between models astrophysically. That depends on looking at the whole ergosphere. We can talk about it later. I have some papers how there are 2 jets, I believe, in AGNs, one from the horizon, one from the ergosphere. And they behave differently. The ergosphere jet, it doesn't go through the horizon, is much more powerful. Yeah, I mean, well, we'll talk about it. This is not for this talk because we'll lose time, but it does involve the infrared and microwave spectra of AGN. Okay, so what I'm going to do is do a proof by induction that the near horizon is not a unipolar generator. So I assume there's this is the key point, I assume there's a pair of perfect MHD leads near the horizon. The key point is I don't demand what circuit it's attached to. It's attached to some circuit. I don't know what it is. That circuit may have voltage drops in it. It may be perfect MHD, which I highly doubt. But I don't know what that circuit is, but it doesn't matter for my analysis. I'm just going to look at the circuit near the horizon, and this is attached to some circuit. So first of all, assume, like Thorne did in the membrane paradigm, that the current would be 0 in the leads. The first thing I want to show is that the radioelectric field is finite, as I already showed the result before, which will mean that you just need a finite amount of surface charge, basically, at the tips of the lead to shield the wall of the electric field. So let's do this. Look at this piece. And so here are the different components of this line integral. Oh, this could be a problem here, getting this on. This is where focus is essentially. Rima, do you know how to focus this thing? No? Oh, here's a. That was wrong. Okay. So this is almost like worthless here. With like a zoom? Whoa. Whoa. Okay. Okay, that's a good idea. So the easiest integral to do is this piece. First, remind you, here's Faraday's law, the 3 + 1 split. And so we look at these different terms. So this term here in the gap right here is just the lapse function at A. It's approximately the lapse function at A over 2 times the surface gravity times the radioelectric field. Okay, this one over here, we get just the frame dragging effect. We pick the contour so close to the horizon that no fields from this problem, electromagnetic fields, have gotten there yet, approached there. Remember, you can always pick a point that's ahead of the flow, so this whole curve is ahead of the flow in any waves that come from it. So all you get, E is just the walled electric field, which dies off like alpha, and so you get just the V cross V frame dragging term. In this one over here, you get the same piece you got up at the pole, the alpha squared over 2 kappa times the electric field in the gap. Plus you get a frame dragging term that depends on the details of the lead now, on the B theta in the gap. And I think I'm going a little slow here. So the B theta in the gap goes like alpha. There's a contribution from the tip, there's a contribution from the walled field, and there's a contribution from the frozen in condition being jumped across the tip of the lead. All of those scale like alpha. People know about Zamo frames, would not be surprised at that result at all. Then we have this piece here, and this is the key piece in this equation, because now we have for this A integral of E dot dl is exactly canceled by the inward motion of flux. This is what differentiates the black hole case from the unipolar inductor, is that a toroidal magnetic field is coming in with E theta. It's like a wave. Any current or charge distribution, like this wall charge distribution to shield the wall field, is moving inward in this case. And so its E theta is always minus B phi, because it's moving inward at the speed of light in the Zamo frames. And so that allows these two terms to cancel, which you don't have in the static case in a laboratory unipolar inductor. Then you have the frame dragging term. The two frame dragging terms cancel out, because they're like the same to alpha squared, and this term cancels out identically, so all you're left with are the little finite magnetic electric fields in the gap. So what we find is that ER is finite in the gap. That's where the ER goes like, oh, I got to unzoom it here. Oops. At least. And then we also have that the shielding on the side of the leads is finite as well, because the wall field E theta goes like alpha, dies off like alpha, so we don't need a large, we just need a very small charge distribution that dies off like alpha on the sides of the leads as well. And so there's also an E theta from the, to be precise, from the amount of charge. Remember we had charges to shield the radial wall field in the gap. That makes the ER. Well, that creates just a finite E theta far away that goes off, dies off like alpha as well. So you don't have any large surface charges down there. You look at all the sources. So the fact there's no large surface charges that are needed to shield this tip of the lead means that you can establish an electrostatic equilibrium in the proper frame of the conductor. No charges need to be taken from upstream to supply an ever-growing surface charge density, first point. Second point is that the radioelectric field stays well behaved so it doesn't pull charges out of the wire and drive a current. What Kip Thorne says is that that radioelectric field will pull charges out of the wires, and the mistake he makes is that he doesn't look at the equations of motion of the particles in the wire. He says we're just going to hold the wires fixed. Well, if you hold the wires fixed right outside the horizon, the electric field will grow like 1 over the gap squared. But you can't use the asymptotic form of the field and not use the asymptotic form of the momentum equations for the particles that make those fields. And that's the problem. When you allow the particles to move in near the speed of light in the Zamo frames, which they have to do near the horizon, you get the B phi equals minus E theta. So the point is that there are no currents flowing in this problem still. I still remains 0. This proves by induction, since we assumed I equals 0 at the beginning, that the horizon is not a unipolar generator. And the near horizon voltage drop is across the magnetic field lines, does not drive any current. And the difference is, again, to elucidate, because it is a fairly complicated calculation to hear verbally, is that you now have E theta equal to minus B phi, so the change in flux inside the contour is canceling out the E dot dl term, which doesn't happen in electrostatics and allowed the radial field to grow. Now, the related thing is that we show the near horizon will passively accept all voltage drops. Again, we do a different problem, but very similar, have the same type of integral. We just assume some arbitrary current is flowing in these lead tips. And we'll expose some more physics in here, and this will slowly lead us into the MHD case. Again, we do our line integrals, the radioelectric field, the same line integral. B theta is still minus E theta, so everything's the same. We have a finite amount of current, a finite amount of charge to screen the radioelectric field of the wall field. But now there's something different. Because there is a current, it turns out that E theta diverges like alpha to the minus 1, and the surface charge distribution will also, on the sides of the tip of the lead, now here's the lead, on the very sides down here, will diverge like alpha to the minus 1. What this charge is, this is really the Goldreich-Julian charge that makes the electric field 0 in a pulsar, for instance. It's what's shielding the conductor from the electric field. Now, just to point out, the voltage drop is arbitrary in this situation because E theta is minus B phi. We can use Ampere's law to get the current. So the voltage drop across the field lines, the integral of E theta across the field lines, is really just a function of I0. So we have an arbitrary voltage drop, set as well as an arbitrary current. The question is the current needed to shield the side of the conductors a unipolar current? As a matter of fact, what I'm doing is I'm saying, look, this isn't a standard unipolar inductor. Has Thorne uncovered something that you don't normally think of as a unipolar inductor, but it's mimicking a unipolar inductor? And that's the point of this calculation. And so if we just look at the little tips of the leads, we do an integral E dot dl outside of the flow front, you can see that the voltage drop across the field lines has to be a constant in that region because there's no voltage drop in the leads themselves. Now, the near horizon, though, will never react back on this voltage drop in the leads that the leads is carrying. It's just the ER stays the same. So the voltage drop, remember ER is just this finite quantity that just approaches some constant. And so no charges are pulled out of the leads. The current never changes due to the horizon. So the horizon is just passively accepting the current and the voltage drop. By contrast, you do the same thing with a unipolar inductor in the laboratory. Unipolar inductor will immediately emit waves and establish the voltage drop as its rotational frequency times the flux and the current. So that's a big difference right there. So this leads to the MHD case. We find when we look at an MHD winds going into the horizon, the near horizon will accept the voltage drop, or equivalently the field line angular velocity, because the E theta is just omega times the colloidal field, omega f times the colloidal field, where omega f is the field line angular velocity. So the horizon just accepts any voltage drop an ingoing wind takes with it. And furthermore, the structure of the ingoing MHD wind front, if you compute it, is identical to an outgoing pulsar wind if you look in the Zamo frame. In particular, there's just one interesting result that comes out in pulsar physics, that the field-aligned colloidal current is equal to the Goldreich-Julian charge density, which sets the electric field, proper electric field equals 0 in the magnetosphere, times the reciprocal of the colloidal velocity. And what this tells you is that the field-aligned current is predominantly just the advection of Goldreich-Julian charge associated with the global potential, just like asymptotic infinity. So now we show that the horizon, this suggests that the horizon, again, just like for the electromagnetic case, is an asymptotic infinity to MHD winds. First of all, the voltage drop between the horizon and the flow front of ingoing MHD wind dies off like alpha squared. For an outgoing wind approaching infinity, the voltage drop dies off like 1 over R between the flow front and infinity. With a unipolar inductor, the voltage drop stays a constant as you bring the plasma flow waveguide towards the disk. Secondly, the horizon passively accepts any voltage drop or field line angular velocity, just like asymptotic infinity of the outgoing wind. By contrast, the unipolar inductor establishes the voltage drop as the field line angular velocity is equal to that of the disk. Electrostatic equilibrium is achieved in the flow front of the MHD wind to shield the wall of the electric field, it turns out. But in the unipolar inductor, electrostatic equilibrium will break down as the flow front approaches, or the plasma flow waveguide approaches the disk. Thus, it's very clear that the event horizon behaves more like an infinity than it does like a rotating conductor. And this is the key point of all the membrane paradigm and its applications in astrophysics. One other thing, this will be very short. Just for completeness, people have conjectured, well, what can mimic the unipolar effect? And this is in terms of charge-separated magnetospheres. And it's an idea of Finney, where he said, so here again is our wall electric field I showed you yesterday. The solid lines are the magnetic field, the dashed lines are the electric field. So, well, look, you go down the pole, here's the electric field's parallel, has a parallel component to the magnetic field that can drive a current inward. Okay? And these parallel electric fields near the horizon, even though there isn't a unipolar inductor there, the parallel electric field in this charge-starved magnetosphere, the magnetosphere, there's not enough charge to short out the electric field. It has to be done by pair creation. And the positive and negative charges are separated, like in a charge-starved pulsar. These parallel electric fields near the horizon mimic the unipolar inductor. The problem is, if you look, now we need a return current, so we have to go to this flux tube, and E dot B changes sign in the flux tube. So here E is parallel to the current flow, but then the current flow has to be anti-parallel to the electric field out here to close the circuit, which is obviously impossible in a charge-separated magnetosphere. And just generally, you would think, I'll go into the numbers later, but if you have 10 to the 41 ergs per second, you'll exceed the Goldreich in gamma rays, you would exceed the Goldreich-Julian charge density in a real situation. That's very likely in an AGN. But let's just consider this anyway, just for a thought problem. Can this charge-star magnetosphere, which probably would never exist in an AGN, drive the current? E dot B is not equal to 0. We can run the current down the pole, as I mentioned, but the return current can't flow because the current has to flow anti-parallel to the electric field. This is the well-known Goldreich-Julian conundrum and in pulsars. And in fact, work by Michael and his graduate students showed that without a unipolar generator at the pulsar, that you would end up with a static equilibrium. The parallel electric fields would never drive a current. And they computed the static equilibrium. It's very difficult to compute. It's all inside the alphane surface. The charge density dies off before you get to the alphane surface. So no charge have to flow out through the light cylinder. So this is the case here. We don't have a unipolar inductor. So the parallel electric fields aren't going to bail us out either. And the lesson learned from this is that we can't understand how a black hole can power a wind by just looking at the event horizon. We actually have to understand the physics in the ergosphere that can drive the microscopic physics that drives those currents. Until we find that microscopic physics, we don't know anything about this problem. And that's the next thing I'm going to talk about. Stand up. You know, I maybe need that microphone. I'm having a wait. I can't. I've picked up like 1 out of every 4 words you said, and I know I could understand you. We were talking last night. We were close by. So, is there maybe if you had a microphone, it might help.
See, when you are dealing with this voltage drop and the finite resistance, resistivity of the horizons and so on, you would expect that the behavior of the outflow to be also universal. I mean, namely that the asymptotic velocity, the mass outflow rate, and the flux of matter that is coming out should have some universal properties, because you are now dealing with the horizon. Generally speaking, people consider that the outflows have really not much to do with the horizon itself, but part of the disk and probably even the outer part of the disk. And so, when you are emphasizing that things going on within a Coaxial radius of the horizon are really dictating the outflows, that you really are committing yourself to explain, to predict that there is some kind of universality in the outflows. But whereas we know, on the other hand, there are large types of, not all the jets are superluminal, not all the outflow rate is close to the inflow rate or even fraction of a percentage. So there is not much universality in the behavior of the jet. But the physics of jet has to do with some universal behavior of the black hole. We don't know where these uncertainties get injected into the model. I mean, that is the problem I am facing. You are going too much detail of the black hole horizon problem and so on, and what I am worrying is whether these are relevant to explain the asymptotic properties of the jet. I mean, I am trying to say that academically this is all right, but I am trying to understand this situation.
Okay, I'm going to try and basically repeat what you said to make sure I understand it. You can tell me if I understood it wrong. I think what you're saying is that you assume that the disk, or a lot of people assume that the disk is more important than the hole for driving force. No, I missed that part. I thought you were trying to say that. Okay, yeah, you don't.
I understand your question quite well. His point is the point. You give me things in your problem. What you observe. I didn't mean you whatever. You should restore the mother physics and to distinguish between two conditions which you have for your mother. And I found this generic formula that people try to do, I don't have one equation, we still doesn't know, and people try to solve equations that not just put unknown, but continuous solution.
Okay.
The
Yeah.
point is what is the invariant of your model.
Okay, let me try again, because I think I was going to say that, so let me see if I'm saying the same thing as you guys. That, first of all, this problem is not, the problem I solve has nothing to do with an outflow. We never talked about an outflow. This is just to see what the event horizon does. You're talking about the global thing. Well, what happens, I think, around black holes? You know, there are lots of different processes going around. How do you differentiate between the two of them? And it's very interesting, and I can give you a reference. But I found that you can differentiate between models. That if you look at the spectrum of blazars, there are two peaks in the spectrum. There's a peak in the centimeter and there's a peak in the millimeter. And if you look at the ratio of those two peaks, it tells you a lot about other properties. It tells you about its gamma ray emissivity. It tells you whether it's a BLAC or a quasar.
That has to do with
It tells you the redshift, basically, when in the universe it was formed. It tells you the optical polarization. And the model I propose is that the horizon wind, although it may be unsteady, it may have all kinds of reconnection, is a weak wind that only exists when you have a lot of rotation, very little rotation, because as Jari Bicak will explain later, that when you have rapid rotation, there's no flux through the horizon. And rapid rotation is usually what we're interested in astrophysically. So the horizon wind has its own properties, and it's a weak wind because the black hole can't grab on to the fluid. The plasma is disconnected far away. The black hole never gets a good grip on the fluid. But the next talk, I'm going to talk about field lines that go into the ergosphere, miss the horizon, and go through the equatorial plane. There, we had no unipolar induction near the horizon, so the ergospheric physics should exist there as well. That drives any kind of wind. You don't need to go through the horizon to drive wind because the horizon does nothing for you. So on those field lines you can have disk condensate, and that disk can stay in causal contact at smaller lapse functions, closer to the hole, and make more rapidly rotating fields. And that's associated with what we normally call the VLA jet. And then I talk about a blazar jet from the horizon that's embedded within that. And it reproduces large volumes of statistical data. Whether these jets are perfectly formed or not is irrelevant. There's an average energy and a time in the evolution of the whole when they would occur.
No, what?
Okay. Hey, Remo, can I ask you?